Hello GATE aspirants. Welcome to part 16 of GATE Quantum Mechanics series. Question number 13. A particle of mass m is in a potential V of x is equal to half m omega square x square for x greater than 0 and V of x is equal to infinite for x less than or equal to 0, where omega is the angular frequency. The ratio of the energies corresponding to the lowest energy level to the next higher level is. So this is a half harmonic oscillator and corresponding energy levels En are given by this expression. En is equal to n plus half h cut omega, where n takes only odd values 1, 3, 5 and so on. So the lowest energy level is for n is equal to 1. So E1 is equal to 1 plus half h cut omega, and that is 3 by 2 h cut omega. And next higher level is n is equal to 3. So E3 is equal to 3 plus half h cut omega, and that is 7 by 2 h cut omega. And their ratio is E1 by E3, and that will be 3 by 7. So option A is correct. Next question. A particle is scattered from a potential V of r is equal to g delta cube r, where g is a positive constant. Using the first Born approximation, the angular dependence of the differential scattering cross section is. Now in the first Born approximation, the scattering amplitude is f of theta phi and is equal to minus m upon 2 pi h cut square integration e raised to minus I q dot r V of r d cube r, where q is equal to k dash minus k. It is momentum transfer. And if we are considering elastic scattering, then mod of k, magnitude of k and k dash will be same. And here V of r is g delta cube r. So f of theta phi is equal to, g is a constant, so minus mg 2 pi h cut square integration e raised to minus I q r delta cube r and d cube r. So this is an integration and it will give us value only when r is equal to 0. So this will be equal to minus mg 2 pi h cut square, and this will be e raised to 0, which is 1. Now the angular dependence d sigma by d omega is equal to mod of f of theta phi square, which will be square of this. So that is square of mg 2 pi h cut square. That means it is independent of both theta and phi. So option D is correct. Next question. Which of the following options is or are correct for photons? Option A, its rest mass is 0 but its energy is non-zero. Option B, it carries non-zero linear momentum. It carries 0 spin angular momentum. It has 2 linearly independent states of polarization. Now photons have 0 rest mass, so it's correct. And energy is h nu, or you can write it as Pc, which is non-zero for finite frequency. So option A is correct. It has energy E is equal to Pc, so it carries non-zero linear momentum as well. So P is equal to E by C, or you can write it as h nu by C. So non-zero linear momentum. Photons are spin 1 particles. So option C is wrong. And photons have 2 transverse polarization states. So these can be expressed as 2 linearly independent polarization states. So option D is correct. So here option A, B and D are correct. Next question. Let M and N denote the energy eigenstates of one-dimensional simple harmonic oscillator. The position and momentum operators are x cap and p cap respectively. The matrix element M, P, X, N is non-zero when. So x operator is x cap is equal to under root h cut by 2m omega a plus a dagger, and p cap is I under root m h cut omega by 2 a dagger minus a, where a is lowering operator. So a operated on n will give us under root n minus 1, and a dagger is raising operator. This will be under root n plus 1 n plus 1. So let's first calculate p x cap. So p cap x cap, and that will be equal to I h cut by 2, and then we have a dagger minus a plus a dagger, and that will be equal to I h cut by 2, and we have a dagger a plus a dagger square minus a square minus a dagger. So let's operate it on n. So first term, a dagger a operated on n, that is root n n, and that will be equal to n. Second term, a dagger square operated on n, that will be root n plus 1 and again n plus 1, so n plus 2 n plus 2. Next, a square operated on n, so that will be root n minus 1 n minus 2, and last a dagger, that will be root n plus 1 n, that is n plus 1 operated on n. So just combine all this. So we have m here, and then p cap x cap n, and that will be, first term is this n, so this will be m n into n plus m n plus 2, then we have root n plus 1 n plus 2, plus next is root n minus 1 m n minus 2, and last term is n plus 1 m n. Now this will be not equal to 0 when these terms are non-zero. So when m is equal to n, so because this is inner product, and that will be equal to delta mn. So when m is equal to n, this is possible. Here m should be equal to n plus 2, and here m should be equal to n minus 2. So only when m is n or n plus or minus 2, then we will get non-zero values. So option B is correct. Next question. A two-level quantum system has energy eigenvalues E1 and E2. The perturbing potential H dash is equal to lambda delta sigma x is introduced, where delta is a constant having dimensions of energy, lambda is a small dimensionless parameter, and sigma x is 0, 1, 1, 0. The magnitudes of the first and second order correction to E1 due to H dash is. First of all, let's write down the unperturbed Hamiltonian, that will be H, and it has eigenvalues E1 and E2, so we can write it like this: 0, E1, E2. And also we have H dash, which is lambda delta sigma x, which is 0, 1, 1, 0. Now eigenvalues of this H is E1 and E2, and corresponding eigenfunctions will be 1, 0 and 0, 1. Now for the first order correction, En 1, that is n h dash n. So we'll calculate that first. So E11 will be, for E1 we have 1, 0, so it will be 1, 0, h dash is lambda delta 0, 1, 1, 0 and then 1, 0. This will be equal to lambda delta and this will be 0, 1, 1, 0, which is equal to 0. So first is 0. So option B is wrong, option C is wrong. Then second order correction, En2. By definition it will be summation over, when m is not equal to n, mod of m h dash n mod square upon En0 minus Em0. So this will be equal to, so m should not be equal to n, and we have this, let's call this as ket1 and this as ket2. So it will be mod of ket2 and we have h dash here and 1 mod square upon energies. So that will be 1 and 2 here. So 1, 0 minus 2, 0. That will be equal to mod of, first is 2, that will be Bra-2, that is 0, 1, then lambda delta, then 0, 1, 1, 0 and then 1, 0, mod square upon E1 minus E2. So if we calculate this, this will be 0, 1 into this, so that will be 0, 1 and 0, 1, 1, 0 is 1. So only lambda delta, so answer is 1. Product of this matrices is 1. So we have here lambda and delta square. So this will be equal to lambda square delta square upon E1 minus E2. And that's because we took 2 and 1 here. If we took 1 and 2 here, then this will be E2 minus E1. So basically we can consider it to be mod of the values, difference of the values. So here option A is correct. This half is not there. Next question. An electron with mass m and charge q is in the spin up state 1, 0 at time t is equal to 0. A constant magnetic field is applied along the y-axis, B is equal to B naught j cap, where B naught is a constant. The Hamiltonian of the system is H is equal to minus H cross omega sigma y, where omega is q B naught by 2m greater than 0, and sigma y is 0 minus I 0. The minimum time after which the electron will be in the spin down state along the x-axis is, and this is spin down state. So first of all, H is minus H cut omega sigma y, and we know time evolution operator is u of t, and that will be equal to e raised to minus I h t by h cut. So let's substitute this value of h here. So h cut will cancel, minus minus will become plus, and we'll have this equal to I omega t sigma y. Now we have psi of 0 at time t is equal to 0, the function is 1, 0, state is 1, 0. Let's call it ket 0. Now we know e raised to I omega t sigma y can be expanded like this. We have cos omega t, then identity function, plus I sin omega t and sigma y. And we will operate this on ket 0. So let's focus on this sigma y. If we operate sigma y on ket 0, this will be 0 minus I 0 operating on 1, 0. That will be equal to 0 I, which is I 0 1, which is, let's call it ket 1. So this will be I ket 1. So psi of t is unitary evolution, so e raised to I omega t sigma y operated on psi 0, but psi 0 is ket 0. So e raised to I omega t sigma y operated on ket 0. But this is equal to cos omega t I plus I sin omega t sigma y. So this is operated on ket 0. So first term will be cos omega t ket 0 plus I sin omega t, and sigma y operated on ket 0, which is I ket 1. So I into I, that will be minus 1. So here we have minus sign and ket 1 here. Now final state should be this: 1 by root 2 1 minus 1. So this will be equal to cos omega t 1 0 minus sin omega t 0 1, which is cos omega t minus sin omega t. And we want this final state to be equal to 1 by root 2 1 minus 1. Now we have 1 minus 1 sign here. This means that cos omega t should be 1 by root 2 and sin omega t should be 1 by root 2, which is possible if omega t is equal to pi by 4. That means t is equal to pi by 4 omega. So that will be the first instant, minimum time. So option B is correct. Next question. A system of 3 non-identical spin-half particles has the Hamiltonian H is equal to A by h cut square S1 bar plus S2 bar dot S3, where S1, S2, S3 are the spin operators of the particles labeled 1, 2 and 3 respectively, and A is a constant with appropriate dimensions. The set of possible energy eigenvalues of the system is. Now this can be written as A by h cut square and S1 2, and then we have dot product with S3. This can be written in terms of magnitudes of S1, 2 and S3. So let's write this as A h cut square is equal to S bar. So we can write S1, 2 dot S3 is equal to half of S square minus S1, 2 square minus S3 square. So these are the operators, and corresponding values will be, for S square it will be S into S plus 1 into h cut square. So energies will be A by this half, and this h cut square will cancel out, and we will have S plus 1 minus S12 plus 1 minus S3 plus 1, and we will calculate all these values. Now individually S1 is equal to S2 is equal to S3 is half, and S12 is S1 plus S2, so it can have values 0 and 1, half minus half, half plus half. So let's consider first case. So we have S12 is equal to 0 and S3 is equal to half, and S is S12 plus S3, that means S will be half. So H is A by 2, then half into half plus 1, 3 by 2, minus 0, minus half, 3 into 3 by 2, and this will be equal to 0. Next case, when S12 is 1 and S3 is again half. In that case, S can have two values, half and 3 by 2. So for S is equal to half, H is equal to A by 2, then half into 3 by 2, minus 1, 1 plus 1, 2, minus half into 3 by 2. So minus 2 by 2 is minus 1, this will be equal to minus A. Third case, S12 is 1, S3 is half, and S is 1 plus half, which is 3 by 2. So H will be A by 2, then 3 by 2 into 5 by 2, minus 1 into 2, minus half into 3 by 2. So this will be 15 minus 3, 12 by 2 minus this. So this will be equal to A by 2. So answer is 0, minus A and A by 2. So option A is correct. Next question. A system of 5 identical non-interacting particles with mass m and spin 3 by 2 is confined to a one-dimensional potential well of length L. If the lowest energy of the system is n into pi square h cut square by twice ml square, the value of n is. Now spin is 3 by 2. So the spin degeneracy G is equal to 2s plus 1, which is 2 into 3 by 2 plus 1, it is 4. So each state can accommodate 4 particles. So n is equal to 1 will have 4 particles, and n is equal to 2 will have the remaining 1 particle. And En is equal to pi square h cut square upon time 2 ml square into n square. So E is equal to 4 into E1 plus 1 into E2. So we can take pi square h cut square upon twice ml square common, and this is 4 into 1 square plus 1 into 2 square, which is 8. So n is equal to 8, and answer given in the answer key is 8 to 8. So these were all the questions from quantum mechanics part of GATE 2025 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.